All right, continuing on with the PACAT chemistry review and talking about VSEPR theory. We really want to start understanding our molecular geometry and, of course, using OpenStax Chemistry 2nd edition. So let's start looking at the structure of molecules. Diatomic molecules, by far the easiest to figure out their shape, always going to be linear. It's essentially that same idea of between 2 points, you can draw a straight line. Same thing's happening here. But once you get beyond 2 atoms, all bets are off. It starts getting more complicated, and in some cases, 3-dimensional. So in all these cases, we just want to think generally about bond distance, or in other words, the length of the bonds, and also the bond angles. So this is essentially, where we want to consider what are the bond angles between these bonds here. We have a double bond here, single bond here, for example, single bond here. And so we won't be looking at bond angles between lone pairs, but only where there are atoms involved. And so with this, we use a theory that is widespread. It's been used for years, and this is the best way to make predictions about what the molecular geometry will be of molecules. And it is valence shell electron pair repulsion theory, or VSEPR. So the idea behind VSEPR, comes up in this name, valence shell electron pair. So we're looking at those electrons that are on the outermost part of the atoms, and then they are being shared between 2 atoms when they're creating a bond. But then ultimately, we have electron pairs that are, to some degree, repelling each other because they are negatively charged. And the net result of the way that electron pairs are repelling each other within a molecule is going to give the most stable configuration, the most stable geometry of that molecule. They will try to get as far away from each other as possible. So there are 2 types of geometries we want to consider as we are marching forward to figure out what the molecular structure is. And the first one is the electron pair geometry. So this is looking at all the electrons that are around that central atom, whether they're bonded or whether they're shared, and then figure out, all right, what's the geometry of just all the electrons? Then we focus in on where the atoms are, and we figure out the molecular structure. What is the final structure geometry of all the atoms in the molecule? All right, so when the central atom has lone pairs, then we do need to consider what the electron pair geometry is and how the molecular structure is going to be different. And something to take note of is that lone pairs cause deviations from these ideal bond angles that happen in a perfect world where all of the electron pairs are equally repelling each other. So something we'll keep in mind as we're looking at these structures and we're looking at where there's bonds versus lone pairs, that lone pair repulsions are the strongest. They will repel each other the most. And then if you have a lone pair next to a bonded pair, that would be second strongest, as opposed to bonding pair and bonding pair, in which case the electron pairs are stretched over the length of the bond more, and so they're not going to repel each other as much. So we've got these lone pairs causing these deviations from the ideal bond angles, and that happens because the lone pairs they're puffed out more and they're taking up more space around the central atom. Again, they're not being pulled along the length of that bond, but rather they're associated only with that one central atom. So as a result, that larger volume then causes them to repel other electron pairs that are around them more. So this is going to be, the next few slides is going to be a summary of showing all the different possible geometries that we might have. And these are the things we want to take into consideration. So we first look at the total number of electron clouds. We can call them electron pairs. So this is just generically these areas, these regions where there's electrons, but we haven't distinguished them between whether they're bonded pairs or whether they're lone pairs. That we're going to talk about in the next two columns, where here we have the number of those pairs of electrons that are bonded and the number that are lone pairs in this column here. So we're going to look first at the situation where there are two electron pairs that are around that central atom. And so these two pairs of electrons here and here are going to get as far away from each other as possible, as we know they do in VSEPR theory. And that configuration is 180 degrees from each other, and that will give a linear molecule. An example of this, carbon dioxide, where here we have a cluster, a cloud of electrons, and we have another cloud of electrons over here. We're not worried about the fact that this is a double bond on each side, as opposed to if there's a single bond involved. We're just looking at a cluster of electrons, an electron cloud, whether it's a single bond, a triple bond, a double bond, whatever it might be. Okay, so here's our one example of when there are two electron clouds. Okay, then we can look at these two examples here and here of when there are three electron clouds, and these are the two possibilities. So we've got where all three of them are bonds and there aren't any lone pairs. And in that case, the way that these three electron pairs are going to get as far away from each other as possible is if they are in a plane and they are all 120 degrees from each other. And here's an example of a molecule that behaves like this. This is one of our exceptions of the electron deficient atoms, boron, that is okay with only 6 electrons, and it can make this molecule here, the BH3, the boron trihydride. Trigonal planar is the name of that shape. Okay, here's another example. We've got, once again, 3 electron clouds, but now 2 of them are bonded, 1 of them is a lone pair. So in that case, we still have that 120, roughly 120 degrees away from each other, bonded pair, lone pair, but because the lone pairs are able to take up that large volume, this lone pair is going to push down on either side a bit, and it's going to cause this bond angle to be less than 120. And along with that, if we look at the molecular shape, we're just looking at what the atoms are. I've always made the atoms, the central atoms, darker colored, and then these peripheral outer atoms are light colored or clear. And in this case, we look at those atoms, and this is called a bent shape. And here's an example, SO2. All right, let's take a look at when there are 4 electron pairs around the central atom. So now we get a geometry that maybe we're not so used to looking at, and especially the challenge here comes with the fact that we're trying to show a 3-dimensional object, but we're confined to 2 dimensions on this presentation. But we're going to do our best. So tried to use perspective drawing here with this bond is coming out at us. So the bond gets larger perspective-wise. This atom here looks closer to us than this one that is going back away in space, and then it's back there. All of these bond angles, I'm only showing one, but all of them are 109.5. And this is called a tetrahedral shape. All 4 of these are bonds. There are no lone pairs. Example of this is methane, CH4. Now, if one of these is now a lone pair, like we see in this example here, and these 3 are all bonds, here's our lone pair. We're going to see less than 109.5 because that lone pair is pushing down. And when we look at the shape of this, this is kind of like a pyramid. It's a stubby little pyramid with 3 legs to it, essentially. So it's called trigonal pyramid. And ammonia is a great example of a trigonal pyramid geometry. And then our last example of when we have 4 electron clouds around a central atom. 2 of them are bonded, 2 of them are lone pairs. And so these lone pairs are going to once again push down on these bonds. And it's going to cause this bond angle to be even less than 109.5. And once again, we have a structure that is bent. We saw this before. The bond angles are different for this, but it still does have that general bent structure. Water, great example of a bent structure that arises from 4 electron clouds where 2 are bonded into a lone pair. All right, and then we have this possibility of when there are 5 electron pairs around a central atom. This is a case where the central atom has expanded its octet, and specifically it's holding 10 electrons. So here we have an interesting geometry. These are not, all these bond angles are not identical. In this case, we've got these atoms that are directly above and below the central atom. We call these the axial atoms. We call these that are around on the middle part the equatorial atoms. And it turns out that the bonds between all the equatorial atoms is 120 degrees, as opposed to the axial and the equatorial are 90 degrees from each other. So it turns out this is called a trigonal bipyramid. And the reason for this is that we can imagine we have 2 pyramids that are essentially stacked on top of each other, where one of them on top, this one, is pointed up, and the one down below is pointed down. All right, another possibility. Here we have the 5 electron pairs around the central atom, but one of them is a lone pair. There's more room in the trigonal bipyramid electron structure. There's more room for a lone pair to take the equatorial position, so it does. It does in a very predictable way, no exceptions. So the net result is we've got these 2 atoms that are above and below, and then we have these 2 that have a bond angle of less than 120 from each other. They're getting squeezed a little because of the lone pair. And if we turn this molecule 90 degrees on its side, we can kind of see better why it's called seesaw. So it's sort of like a seesaw. It also could be called a teeter-totter or sawhorse. Lots of creative names for this. All right. And SF4 is a good example of this. Sulfur tetrafluoride, where those fluorines are all in these positions out here. All right, we can also have 2 lone pairs. All right, we still have this same axial equatorial situation. Lone pairs are always going to take the equatorial position. And if we turn this molecule on its side or turn it 90 degrees, we can see that it looks like the letter T. So this is called a T shape. And one example of this is chlorine trifluoride. Okay, and we're almost done with the summary. And this is when we have 6 electron pairs that are around a central atom. And if there are no lone pairs, we end up with a symmetrical molecule that is an octahedral shape, we call it. And here's an example, sulfur hexafluoride. If we have 1 lone pair, it's going to take one of those positions, and the net result is a square pyramid. So that lone pair will cause a little bit of pushing up on all these atoms down here. That causes this 90-degree bond to get a little bit smaller. But for the most part, it still looks like a square pyramid. And here's an example molecule of that. And then our final example. If we do have 2 lone pairs on a situation where there are 6 electron clouds around the central atom, the other lone pair is going to try to get away from the other one as much as possible. And so the best location is directly opposite it. And so the net result for our geometry is square planar. In this case, we do have exactly 90-degree angles between all of these because those lone pairs are symmetrically opposed from each other. All right, so here's one big summary of all those situations that we talked about. I'm not going to go over this. I'm not going to march you through it. You can take a look at it, but I just wanted to make sure that it was here so that you can refer back to it if you wanted a concise place to look at all the possible geometries, depending on the number of electron clouds, lone pairs, all those kinds of situations. All right, so how are we going to do this? How are we going to figure out the structure with VSEPR? And a starting point always, we need to draw the Lewis structure. We need to have that to be able to start out knowing how many electrons there are, how many bonds there are, and where are the lone pairs. And from there, we can use VSEPR to figure out what's going on. So in terms of those electron clouds or those electron regions, as I said earlier, we do consider each one of these, whether it's a lone pair or some kind of bond, doesn't matter what kind of bond, those all count as one region. That allows us to identify the electron pair geometry. And then from there, the most important thing is to take the final step and determine the molecular structure. So it will have the same geometry as the electron pair geometry if there are no lone pairs. But if there are lone pairs, those are essentially considered to be invisible in terms of they're affecting the geometry, but they're not dictating what the final molecular geometry is. So we just take them into account as we're figuring out that final geometry. So let's take a look at ammonia. All right, we looked at ammonia earlier, but if you've forgotten already, we can kind of reason through what's going to be happening here. So if we're trying to figure out the molecular structure, got to have that Lewis dot. Okay, so that's our beginning point. And again, we get this from adding up all the valence electrons. That's something you can get from the periodic table. Nitrogen has 5 valence electrons. Each hydrogen has 1. So because there are 3 hydrogens, they are contributing a total of 3. And since nitrogen has 5, we have a total of 8 valence electrons in this whole molecule. So the nitrogen's got that octet. All 8 are being shared by nitrogen, and all of the hydrogens have their duets or their pairs. So it's all stable, it's all good, and we can move forward. So we consider what happens when we have 4 electron clouds, electron regions around a central atom, as we do in this case. And that means the electron pair geometry is going to be tetrahedral. Okay, but again, that's just our stepping stone to be able to then figure out what's the molecular structure. We identify the lone pair. We acknowledge that it is essentially invisible. We can think of it as a cloud, an electron cloud. Okay, whereas it is not a solid, that solidity that the nuclei have in an atom, that's going to dictate the molecular structure. So then when we look at the final structure of ammonia, we see that it is trigonal pyramid. The bond angles here, because of the lone pair that's up here, we're just, we know that it's there, but here we're just looking at the geometry in terms of where the atoms are. But that bond angle is going to be squeezed a little bit, so it will be less than 109.5 because of the presence of that lone pair that's up here. We can do the same with methane. So methane, again, starting out with a Lewis structure and then moving forward. So here I wanted to show the previous slide had drawings that you wouldn't realistically sketch very easily if you're not a good artist. And to do chemistry, you do not need to be a good artist, but we do want to have a way to show that this is not just flat. This Lewis dot structure here looks like it could be just a two-dimensional square kind of geometry. We want to show that this is three-dimensional. So we do that with wedges, which is essentially thick lines coming out towards us, showing that three-dimensional, that hydrogen coming out of the paper, out of the board, out of the screen towards us. And then the dashed lines show it going back behind us. So electron pair geometry, tetrahedral because there are four around it. There are no lone pairs. So in this case, the molecular structure is the same. It is also tetrahedral. And our bond angles, we can expect them to be exactly 109.5. So in terms of polarity and dipole moment, okay, so we mentioned this in the previous section, that if we have a polar bond, if we have a difference in electronegativity of the two atoms, we're going to end up with what we call a dipole. A dipole is showing a separation of charge. And the result of this, we can use this noun here, a dipole moment that has the symbol mu. This means that we do have this separation of charge. And the more polar it is, the more asymmetry there is with the electron density, the larger the dipole moment. So it can be expressed as a vector. We saw this before, where the arrow is pointing towards the more electronegative atom. Now, I did mention carbon and hydrogen have very similar electronegativities, and this bond is considered, for the most part, to be nonpolar. But the point here is that it is nonpolar for all intents and purposes, but it is ever so slightly polar. And so we can show this small polarity by just showing a very short arrow. And so that difference in electronegativity being really small, it's a very small dipole. That's why we can ignore it for the most part. As opposed to if we have a molecule that has fluorine in it, oh my gosh, it's really very electronegative. So it will be pulling electron towards itself, and this will be a long vector, a large dipole moment in this case. So if our molecule has an overall molecular dipole moment, then the molecule overall is considered polar. So it's got that partial positive on one end, partial negative on the other. If you have a nonpolar molecule, then no negative or positive poles. Don't need to worry about it. So in terms of trying to figure out, is the molecule overall, is it going to be polar or is it nonpolar? And very straightforward if you have a diatomic molecule, just having two atoms in it. If the bond is polar, if there is a difference in electronegativity, the molecule is polar. And follows that if the bond is nonpolar, molecule is nonpolar. Okay, but once we get a little bit more complicated, then we need to look and see what's going on. So if the molecule has at least one polar bond, then we have an indication that we could have a polar molecule. But also with that, the molecule has to have an overall dipole moment. Okay, so let's take a look further at this. So a molecular dipole, if we don't have both of those criteria I just mentioned, if they're not met, then we have a nonpolar molecule. So we do need to figure out the molecular geometry and consider it when we're looking at the overall dipole moment. So this is the thing. Some bond dipoles will cancel each other out. So even if you have polar bonds, if they cancel each other out, overall the molecule will be nonpolar. And so if you have, for example, we're just distinguishing between two atoms by calling one A and one of them X. And if they are arranged symmetrically around the central atom, then that's a case where those polar bonds will cancel each other out. And overall, you get a nonpolar molecule. So with that, there's our material for bonding, molecular geometry, and VSEPR theory.